Yes, good afternoon. I'm sorry I'm a bit late. Somebody just confirmed to me that you can hear me, please. Anybody can switch on the mic, including the CRs. Adino Paul, can you hear me? Just switch on your mic.
Yes, I can hear.
Okay. And is Moses there? Let me check. CR, are you there? Any of the CRs? I'm seeing only 20. Oh, Gola. I'm seeing. I can't see any of the CRs. Okay, we'll start. Yes, give me some time. I'm trying to set up my student computer. Okay, things are okay now. Instead of clicking today's class, I was clicking yesterday's class at the same time. So I was wondering why it was not connecting. So I hope everybody can see the presentation on the screen. So we are starting a new topic, which is DC voltage regulators. DC voltage regulators. Now, before entering this new topic, I'd like you to, in your free time, just use Google search and search for the IC-based multipliers or manufacturers of IC multipliers. So we've seen a few, like that of Motorola. There are some other companies which also manufacture. And just go and check their configuration. Look for the internal circuitry, and you'll be able to spot a Gilbert's multiplier inside. And just look how they bias the circuit. And maybe from the application circuit, find out the quiescent currents flowing in the circuit when it's biased properly. Okay, so today we are starting a new topic, which is DC voltage regulators. So a regulator is something that regulates. So if in case of voltage, it is constant. We have different types of regulators and have pressure regulators, etc. But here we are going to be dealing with direct current voltage regulators. Now, I've introduced this topic by saying that most electrical and electronic equipment require specific voltages for their operation. Hence the need for a regulated DC supply. For example, in industry, the following processes require fixed voltages. So things like electroplating, arc welding, which requires a voltage of about 47 to 67 volts at various currents ranging from about 100 to 250 amps. Of course, in arc welding, there are various types of arc welding. There's what we normally call the stick welding that you normally see the Juakali people using to make doors, windows, etc. Then there's the metal inert gas, normally called MIG welding, which is normally used for fast welding. So if you want to weld many things in an industrial process, because with stick welding, each time the stick gets finished, you got to change it, it wastes time. With the MIG welding, normally you have a spool which is inserted into the welding machine, and as you use it, it rolls. So there's no time wasted changing. In the case of changing the stick, so it's called MIG because it's a metal inert gas. Normally the output of the welder, apart from outputting the stick, the core, we call it the welding core, there'll be a gas, normally argon, which flows through the tip of the welder so that whatever the metal you're welding does not oxidize. And the last part is the TIG welder. So for very special processes, like welding stainless steel, they normally tend to use TIG. So it's a more fine type of welding, but it's time consuming. Number 3 is in chemical industries, things like electrolysis, say things like purification of things like copper, electrolysis or chemical purification. We need fixed voltages in universities, electronic equipment, things like your computer. If you've assembled a computer, especially like a desktop, you'll find that there's a power supply which takes power from AC and outputs lots of voltages. So one of them would be like plus minus 12 volts, which are used for things like the hard drives. And then you have things like positive 5 volts, which are used for various parts of the motherboard and maybe the cards which are inside, connected to what is known as the PCI bus inside the computer. And then you might have maybe plus minus 3.3 volts, which are used for the processors. Now, in third year, if I taught you instrumentation, things like the cathode ray oscilloscope, we find it, there are so many, the power supply produces so many voltages, most of which are DC, which range from maybe 200 volts, 800 volts, to almost 2,500 volts to accelerate the electron. Then in laboratory power supplies, like the ones used in the labs, you'll have power supplies which may output plus minus 15 volts or plus minus 5 volts when you're dealing with TTL. Then at home, for domestic applications, you have your TVs, your DVDs, your laptop chargers, your phone chargers. All this require regulated DC supply. Now I'm just wondering why there are so few of you. CRs, any of the CR, can you tell me? I'm only seeing 28 people. Even up to now, what's the problem, CR? Moses, are you there? Moses is not there. And the lady CR, are you there? They're not there. Anybody can stand in for this year and tell me why there's only 28 people, 28 students? Anybody? Yeah, switch on the mic.
It might be because the Sihar has not shared the link. He usually shares the link in the WhatsApp group. Maybe because now they're not here, maybe the rest do not know there was a class.
No, but see, you just go to your calendar. See, most of you have got smartphones, and the calendar displays on the smartphone, isn't it?
Yes. Allow me just share the link with them.
Okay. Because I don't want to go through this again. Okay, so we'll continue. So I've shown you one of the reasons why we're going to study this topic. There's industrial applications. There is academic applications. There is domestic applications. I'm sure all of you have got phone chargers. Most of you, all of you have got laptops and TVs at home. So if you've got things like smart TVs, you'll find there's a processor inside. And these processors may be using 3.3 volts for their proper operation. Then there are various parts of the television which also need various voltages. And a lot of you charge your phones in the morning, maybe before you come to class, charge them at night. So those those phone chargers typically give out 5 volts to charge your phone. Unless maybe it's a type C, which has got some other voltages. But most of the phones tend to use 5 volts. Okay. Now, regulated DC supply systems of many types, and the type of control scheme used for a particular application depend on the following factors. Number one is the feasibility, i.e., is it suitable? Is it portable? Is it practical for that particular application? So let's take the example of a phone charger. So like a phone charger, it's going to be very light. It's going to be very small. So if the input voltage is 240, you need to get your 5 volts at the output with a very portable system, a very small system that is easy to carry about. The same will apply to things like laptop chargers. So the other important thing is the efficiency. How efficient is your DC supply system? Normally, you'll find like for things like phone chargers, like the phone chargers that you plug into electricity, do not need to be so efficient, although they still use an efficient scheme. They still use an efficient scheme to try and minimize the heat dissipation. For those of you who don't know, you can check how efficient your phone charger is just by touching it when it has charged for quite some time. The hotter it becomes, the less efficient it is, and the more likely it's going to break down. If your phone charger gets spoiled and you go and get a replacement phone charger, which is not of the original manufacturer, you'll find that one heats up so much, and within a very short time, maybe 6 months, it's dead. The same apply with laptop chargers. If you get the original one from the company, if you use the laptop for a long time, maybe 1 hour, 2 hours, it won't heat up so much. But if you use what is called the replacement chargers, which are quite cheap, they heat up so much. Now, the problem with heat is that we have capacitors inside those laptop chargers, especially electrolytic capacitors, which use an electrolyte, and that tends to evaporate. And with time, all that electrolyte, due to the heat, has evaporated, and then your system will just blow up. Your charger will just blow up. So efficiency is quite important. And the more efficient it is, the smaller the size also of that particular charger. Then there's the mechanical construction. This one depends on application. If it's supposed to be used in an environment which is very harsh, then of course, rigid mechanical construction is very important. Then there's what is known as the speed of response of a particular regulator. In other words, how fast does it detect that the input voltages has changed so that it can correct itself at the output. The faster the response, the better. Because, for example, you might find that the AC input that's coming in, it fluctuates, maybe 180 sometimes. When there's big load, it might reach maybe, when there's less load, it might go back to maybe 240. So the input voltage range may range from maybe 180 volts AC all the way to 240 volts. So when there's a great load in the line where your system is connected to. How fast is the response? How fast does your regulator regulate the voltage? And then next is the cost of design. The cost of design of the protection circuit. If you got something expensive like a desktop computer or a laptop, you should always incorporate a protection circuit, because when a device blows inside your DC regulator, it might give more than the required intended voltage at the output and destroy all the circuits which are connected to it. So for things which are expensive like laptops, desktop computers, protection circuits are very important. And the protection circuits are very important. So those are some of the considerations that you've got to take into consideration when you're designing a DC regulator. Next, I've said that for more accuracy at the output, closed loop control is usually employed and is classified into two groups. One is the AC regulators, and the other is the DC regulators. Now, our course is mainly DC regulators. But I've just introduced it a bit over here that in AC regulators, or in the AC regulation scheme, the control element is normally incorporated on the AC side of the main rectifier. So I've drawn some rough sketch over here. So this space I'd left it to draw a diagram, but I've just drawn a simple one here by hand. So for example, you got 240 volts coming in on the left-hand side here. This is your transformer, your step-down transformer. So your step-down transformer, the secondary has got many tappings. It's got many tappings. And you got a switch which can be controlled by this control element over here. And this control element samples the output. The output is V0, so the output is the output between this positive and negative V0. So beta V0 is a fraction of the output sample to monitor the output. And this is your bridge rectifier. And then your smoothing capacitor over here before the DC regulator. So in AC regulation, this control will be taps, changing the taps of the secondary of the transformer dependent on the output voltage, to control it to the prescribed value. So that is what I mean that in the AC regulation scheme, the control element is incorporated in the AC side of the mains rectifier. So I've just brought this in. This is what sometimes they call voltage stabilizers, which are used for things like fridges, etc. Not the small electronic one. This one normally incorporates a transformer. So it's bulky and heavy. So this is one scheme. There are actually 4 schemes. I would think I've imported some schemes over here. So this first diagram over here they're using a servo motor. So this is your control circuit over here. This is your control circuit over here. It monitors the output. So you get an AC output here, which is constant. You got an auto transformer here, and the servo motor changes the tapping depending on the AC side of the voltage. So if the voltage falls, the tapping is moved upwards to add to this other transformer over here, which adds to the AC voltage. If the voltage drops, then the servo motor is driven to the bottom part. There's also another scheme by using SCRs shown over here. So each SCR has got different tappings. Each SCR has got different tappings. So the topmost SCR, when it is switched on, you'll get the highest voltage. The bottommost SCR, when it is switched on, you'll get the lowest voltage. So using this controller over here, you can monitor the AC output and switch the appropriate SCR. Actually, the way they're connected, the gates are connected here is not 100% correct. The controller, each of the SCRs is controlled individually. They're not all the gates are not connected together like this. They're controlled individually. So that if I switch on the top SCR over here, then the output voltage is highest. If I switch on the bottom SCR, the output voltage is lowest. So if the input voltage increases, I switch on the bottom SCR to lower it. If the input AC voltage decreases, I switch on the higher SCR so that the voltages increase. Now the disadvantage of this AC scheme is the response time of the circuit elements used are slow, i.e. ACRs, line transformers, switching relays have low switching speeds. In other words, to change all these contacts, devices which are used are fairly slow, maybe apart from the AC using ACRs, which could be slightly faster. But ACRs still are not as fast as transistors. But this is just by the way, this is not our course. Our course is DC regulators. Our course is DC regulators. So in DC regulators, the control circuit is incorporated on the DC side of the mains rectifier. Okay, the mains rectifier. So those of you who might not know, normally for most circuits, even your computer, your laptop, etc., you'll have your AC coming in. Then for some of them, say like in the case of lab power supplies, the old lab power supplies, the heavy ones, you'll have a transformer always. Then it goes to a bridge rectifier. Then you have your DC here. In things like computers, you'll have your AC. And then you have your bridge rectifier. So it rectifies the 240 volts direct. We shall see some circuits. So after all of this is when you have your regulator. You have your DC regulator. So our topic is this DC regulator. My topic is that DC regulators. So I've shown a circuit over here, which I've poached from Texas Instruments. So this is the Texas Instruments UA 7800 series. So these are the IC. This is actually an IC. So in the labs, you have like the 78005, which is a 5 volts regulator. You have the 78012, which is a 12 volts regulator. This is what is inside. But actually, it's just a 3-pin device. When you buy it, it looks, it's So it will have maybe the ground. The way you connect it, you'll have one point with the ground. You have one point which is the positive V in, and then you got one point which is V out. Okay, the manufacturer will tell you how to apply it. Maybe you need some capacitors to prevent oscillations, both input output. So this output can either be 5 volts if it's the 7805, it can be 12 volts. There are many series, and there are many companies that manufacture them. So this is how it looks in the inside. Okay. So here, so this device over here, you normally put it here. You normally put it after the bridgeifier. You can either put it here in this one, or you can put it over here. But we shall see for things like computers, it's not, you don't normally use a circuit like this one because the voltages will be very high. And we'll use a new technique which we shall study later on. Okay, but the control circuit is incorporated on the DC side of the mains. Actually, there's an S missing of the mains rectifier. Okay, so this is the these are the mains rectifier, which is just a bridge diode. The mains rectifier they're just diodes. And then normally there are many techniques of doing it, but the simple way is just to use the normally it's already fabricated into one chip. Sorry. I want the positive to be on top. Then I want negative, sorry. I want negative to be at the bottom. So this will be a positive, this will be a negative, and the AC between these 2 points. So this point A and B will be AC. Normally it's just a chip, a block to convert AC to DC. Then you go to smooth it with capacitors, then you apply to your DC regulator. So I've just drawn for you this circuit. Not drawn, this one I've just captured it from Texas Instrument, because this is a common IC we use in the labs to produce 5 volts for your digital circuits. So even those equipment that we have in the labs for digital testing, they use this IC inside. Okay, so this is the internal circuitry of the IC. So we shall see how a similar circuit to this one works. Okay, it will have maybe 5 blocks, which you shall see later on. Okay, so the input here, you got a reference. This is in a diode. You need a reference. You need this an error amplifier. And then you need the control element over here. This is a series control element. This is just an introduction, so we won't go into the details right now. So we're introducing DC regulators. So the regulator of this type is known referred to as a linear regulator. A linear regulator. We shall see why. It's because actually the control element, the voltage across the control element varies linearly with the current across the control element. In this case, these two transistors, it's a Darlington, forms our control element. So you can see input. So these are the 3 pins input. So this will be like our Vin over here. Output is like our V0 over here. And the common is like this middle terminal over here. It's a very cheap and effective method which saves a lot of space. And there's so many components inside, and it's still very cheap. It's still very, very cheap. And there's so many transistors inside. If one of you was to go to Sagana to buy a transistor, maybe the cheapest transistor there will be 50 bob. Maybe it will be around 50 bob, 50 shillings. And if you look at this socket, it's got, say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 transistors inside. So 17 times 50 is almost 600 shillings. But I'm sure this thing you can get it for maybe about 100 bob or less. So if you had to build this circuit using discrete components, it would be very expensive. Okay, so this is one type of DC regulator. We shall see the inner workings later on, the simplified version of this one. And the other type of DC regulator, I also pushed a socket over here, is known as the switching regulator. It's known as the switching regulator. Now, your laptop charger, your computer power supply, your phone charger normally uses this topology over here. It normally uses this topology over here. So the AC comes over here. For example, this one is written 85 AC to 400 AC can come in. Now this is your bridge rectifier. This is normally just an IC chip with four diodes inside, as I've drawn. A simple filtering circuit. Then it goes to this transformer. This is a switching transformer. A switching transformer over here. And you can see this when you rectify, like in Kenya, this would be normally our average is 240 volts. And when you rectify, it comes to about 300 or 340 volts. So all these capacitances should be able to withstand 340 volts. So the DC from the ground to here is about 340 volts. So it will go to this high frequency transformer. And this diode and this capacitor and this resistor is known as a snubbing circuit, which will dissipate energy when the transistor is off. The switching transistor is off. So between what is called D and S over here, the drain and source. So these are the contacts of your switch. So actually, you've got a semiconductor switch over here, which is just a MOSFET. And to use most high voltage MOSFETs, which its function is just a switch. So you can just equate it to a switch, which closes and opens dependent on the frequency that this thing is designed to work at. And then it's got some feedback from this LED over here is actually incorporated inside here. It's just one chip, which is called an optocoupler. So this way you can isolate, instead of tapping the output to sense the output voltage, how much it is, so that you can control it. You don't have a physical resistor or a physical potential divider resistance over here to sample part of the output and feed it to your control circuit over here. We use light instead, because this DC that's going to power your thing, it could be your laptop or your computer or your television. Human beings tend to hold them, and you don't want them being electrocuted. So we isolate the side that goes to your laptop or your television or your phone by getting information about the output voltage by using an optocoupler. So the light from this device over here goes back to this transistor over here. And this transistor will change what is known as the pulse width of the driving voltage over here. So for example, if the output voltage was to increase, there'll be more light produced by this LED over here. The more light is produced over here will turn this transistor here on more. And when it turns it on more, what is going to happen is that the pulse width will become narrower. The pulse width will become narrower, so that if initially said like the pulse width was said like 50%, in time on, time off was 50%, and the voltage suddenly increases, then the frequency remains the same, but the pulse width will now become narrower. And therefore, the average output voltage will decrease. Now, this other second circuit over here, these are the second circuit comprising of this diode, this capacitor. This is used to power the device. It's going to VCC. So once the device starts, it's now being powered by part of the energy that is used to drive the output. That's the function of this diode, this second diode over here. This capacitor, you can see it's going to VCC of this chip over here. Okay, so later on we shall study switch mode power supplies. But this is the architecture of most power supplies, which are known as switching power supplies. Isolation is very important between the output and the input, because the output goes to drive your device. And since we humans, we touch the device, we don't want to be electrocuted if something goes wrong. But this side has got a very high voltage. So we sampled information about the output voltage using an optocoupler. In some circuits, some circuits we shall see, we will sample the output voltage just using a resistor. So this is known as a switching regulator. Now there's a very popular everywhere, because the higher the switching frequency that you use, the smaller the transformer you can use for the same power output. And therefore the power supply becomes very light. And since the windings of these transformers are very few, you save a lot in terms of copper, save a lot in terms of weight, and therefore they're quite cheap as compared to the normal iron core transformers, which are very heavy. You need lots of windings and therefore more expensive and more difficult to transport. So this is the other technique of making DC regulators. So there are two techniques. One is to use linear regulators like this one, and the other is to use switching regulators like this one. So your television, the power brick in your laptop charger, computer power supply will all use this configuration. Which is a switching regulator. This one has got so many advantages, because the output is obtained using a transformer. You can have many windings. So I can have a winding of 3.3 volts. I can have a winding of maybe 5 volts. I can have a winding of 12 volts. I can have a winding, I can have a center type winding, which gives me plus minus 12 volts. So this is very versatile. This technique is very versatile. Okay, so let's go back to our notes. So I've said, sitting here, for DC regulators, the control circuit is normally incorporated in the DC side of the rectifier. and SCRs, which stands for silicon control rectifiers, IGBTs, insulated gates, bipolar transistor, and GTOs, which are gate turn-on devices. So those of you who are doing power electronics will know these devices. So these are the switching devices which are normally used in high-powered applications, while BJTs and MOSFETs are used in medium to low power applications. So low power means from 1 watt to 100 watts. There's also micro power applications, which is from 1 milliwatt to 100 milliwatts. So there's some applications which require very low power. You can also use this. So for example, for driving things like LCD screens, which are very small, you can use that. Then for very high power applications, up to select 200 megawatts, MOSFETs and MOSFETs. I should write MOSFETs, comma, IGBTs, and then I can write and GTOs. And GTOs are used. Can anybody studying power electronics give us some examples of this where we use powers? Let's say 100 megawatts, 200 megawatts. Anybody who studied power electronics, that's what you're doing power electronics. Give us some places whereby would you require powers like this. This is you doing power. So all of you are supposed to do power electronics, is it not? I think so. All of you are supposed to do power electronics. Is it not true? Sierra, are you there? I can't find Moses today. Okay, let me ask somebody here. Emmanuel Otieno, are you there?
Yes, I'm in.
You do power electronics, right?
No. For me, I do telecoms instead.
So power electronics, I thought it's supposed to be common for you people.
No, it's not.
Okay. So give me a friend of yours who does power electronics. It gives us an answer. I can see Gadeka, Nicholas.
Kivuva. Kivuva.
Yes, Kivuva, switch on your mic. Kivuva, switch on your mic. Whatever those people doing telecoms nowadays is necessary to do power electronics. How do you design your power transmitters? How do you design your power transmitters? If you go to Ngong Karen, you'll find the transmitters there for shortwave radio. And the power is about 10 kilowatts. So Kivuba, could you tell us? Okay, I'll give you an example. So for example, everybody knows about the famous electric car known as the Tesla, right? Okay, the larger variant is referred to as the Model S, right? Which have got motors. Some of them have got dual motors, which is about 1,000 horsepower. So which is 1,000 horsepower. So 1,000 horsepower is how many kilowatts? 1 horsepower is 740 watts, right? Or 0.7 watts. Isn't it? 1 horsepower is 0.74 watts, 0.74 watt kilowatts. Is it not from? So if 1 horsepower is 0.74 kilowatts, so if you got a Tesla What is it called? It's called a plaid, I think. It's called a plaid. If it's got 1,000 horsepower, so times 0.74, so that is 740 kilowatts, which is 0.7 megawatts, right? About 0.7 megawatts. Now, Tesla normally, if you look at the inverter that they use inside there, they normally use 400 volts DC. I don't know whether it's 400 or 800 volts DC. I think it's either 400 or 800 volts DC. I've forgotten. Because I think the Porsche is the one which uses 800 volts DC. But the switching devices they use are actually MOSFETs. They actually use MOSFETs made by Infineon Technologies. Now, the DC chargers for these cars give you the superchargers to charge these cars very quickly. You'll find one DC charger can maybe charge maybe 3 or 4 cars. And therefore, if each car let's assume each car takes about 500 kilowatts of power. Then if you have 500 times 4 cars being charged, that's 2 megawatts of power. And nowadays, Tesla and also these Finnish companies like Scania and Volvo, they're making lorries with very large battery packs at 800 volts. So those DC chargers will be outputting some very serious power in the megawatt range. The same applies to these fast trains that they started with the French people, then the Japanese, I don't know what it's called, the Shenzhen, I forget the name, but starting with S. Then the Chinese are also producing them. These trains that go very fast, almost 500 kilometers per hour. The DC motors there output some very serious power to enable those trains move at 500, almost 500, maybe it's around 450 kilometers per hour. So those ones that will be using mainly IGBTs and GTOs. Okay, but that is just by the way. So in practice, for medium power applications, normally we use MOSFETs and BJTs. But BJTs normally nowadays are not used so much because MOSFETs are more efficient. And the technology has really grown for MOSFETs. BJTs tend to have an offset voltage, and that tends to lose power. So nowadays, they're rarely used in the high current applications. But for low power applications, they're still being used. And I've said these regulators are broadly classified as being linear, and switched. I'll show you that. So the linear regulators are normally of 2 types. You have the series and the shunt. And in the series means the control element, what we call the control element, which is the varying resistor, is in series with the supply and the load. In the case of shunt, we shall see the diagram. This control element is in shunt between the supply and the load. Finally, I've said that the function of every DC regulator is to convert an input voltage, or more correctly, I should say an input unregulated voltage, to a specific stable DC output. Do you people have a class after this? Do you have a class after this? I was late by 8 minutes, so let me continue by 8 minutes. So the function of every DC regulator is to convert an input, more correctly here, I should say, an unregulated, convert an unregulated input voltage to a specific stable output voltage and maintain that output voltage over a range of load currents. And over a wide range of input voltage conditions and temperature conditions. To accomplish this task, a typical DC voltage regulator, it could be series, it could be shunt, it could be switched, consists of the following elements. Number one is the voltage reference element that provides a non-stable voltage level, which is called the VREF. Number two, a sampling element that samples the output voltage level. Number three, an error amplifier that compares the output of the voltage sample to a reference voltage and creates an error signal. And number four, a power control element that provides conversion of the input voltage to the desired output voltage level over varying load conditions as dictated by the error signal. Wow, I've read a lot over there, but it's actually very simple if you do it in a diagram. So this is in a diagram form, this is what it means. That a regulator, the left-hand side is your input, which is our unregulated DC input. We have our reference. So this block over here provides a reference voltage, which normally goes to one of the inputs of the error amplifier. So you have an error amplifier, you have your control element over here, you got your sampling element. So these are the 4 blocks that constitute a voltage regulator. So the sampling element samples part of the output voltage. Normally, in most cases, it's just a resistor that forms a potential divider. Okay, so that if, for example, the output voltage is V0, then if you have a resistor, in most cases, just use 2 resistance, maybe R1 and R2. So this is connected to your V0, and this is connected to your ground or your minus voltage. So the voltage here is sampling your sampled voltage will just be V0 into R2, R1 plus R2. Or sometimes you just call this one beta V0. So that's your sampled voltage. So that's how we we normally make a sampler, here sampling element. If you're dealing with high voltages, then which can electrocute somebody, then we use a different technique like the one I showed earlier on in the switch mode power supply. Your error amplifier is normally like an op-amp, and your control element is normally a transistor. It could be a Darlington transistor, and your reference element is normally a Zener. The reference element here is normally a Zener. So this is normally a Zener, which is biased correctly to give us that. Okay. So this is normally an op-amp. And the control element, this is a transistor. So here, given the application, so if you look at this circuit, so that I don't have to read, the function of the sampling element over here is to take, the function of the reference element is to take the output voltage. Remember, this output voltage is still varying, although it's DC, it can vary, but to give a very fixed reference voltage. So the output of a sampling element, we normally call it Vref. The output of our sampling element over here, we normally call it beta, which is a fraction of the output, V0. And therefore, the output of our amplifier, of our error amplifier, because it amplifies the difference, this, I'll call it V dash, be equal to the difference gain into Vref minus beta V0, typically. So the reference element, its function is to give a very stable reference, which is the fluctuations of the error amplifier amplifies of the two voltages, the sampled voltage and the reference voltage. The function of the error amplifier is to amplify the two difference, so it can make correction when it's driving the control element over here. So I'll save myself from reading that. So here I've given the functions of the various elements, starting with the reference. So if I start with the reference element, I've just drawn eyes created. You can read that so we don't waste time. So a simple way to generate a reference element is just use a Zener diode and bias it correctly. The low Zener voltages come with 2.7 volts, 3.3 volts, 4.7 volts, I think 5.3, etc. Okay. So when you're biasing a Zener, you got to ensure that you bias it within its specifications. Normally, the manufacturer will give you what is known as IZ max, the maximum Zener current that you're allowed to pass through it. Then they'll also give you what is known as the power, the maximum power. The Zener can dissipate because when current is passing through it, it heats up. And most semiconductor devices are not happy when you pass about 50 to 56 degrees centigrade. So the manufacturer will give you that information. Most manufacturers tend to give you information at 25 degrees centigrade. So when you're designing a circuit, you got to ensure that you're within the manufacturer's specifications. So for this simple circuit over here, if you bias this circuit correctly, and Vz is less than the supply voltage over here, the voltage across the zener will be Vz. This can be taken as your reference voltage, as long as the circuit is designed correctly. So I've given a simple example over here. I know my writing is terrible because I write with my laptop screen upwards, not downwards. But I think you studied Zenas in your third year. I'm very sure you must have studied Zenas in your third year. So for example, if you check the data book and you find that IZ max is equal to say 0.1 amps, and power zener max no, just give me a hypothetical example over here. So, and let's say that the zener voltage Vz is 3.3 volts. Then it means that PZ max will be 0.1 times 3.3. So this is 0.33 watts. So if you were to design this reference voltage from 10 volts, how do you design for R? So one way to design for R implies, in this example, if it's 10 volts minus Vz over R should be less than 0.1 amps. But Vz is 3.3. So 10 minus 3.3 over R must be less than 0.1. So this tells me 6.7. Well, this tells me that R should be greater than 6.7 or 0.1, which is 67 ohms. So if you check in the data sheet, you're designing a reference voltage of 3.3 volts. So you picked a 3.3 volts zener. From the data sheet, you saw that the maximum current allowed is 0.1 amps. And therefore, the maximum dissipation is only 0.33 watts. Then you design for R, then R must be greater than 67 ohms. And normally, we don't use such a low resistance for R. Because this circuit will be part of our power supply. So you got to consider the power dissipation of this reference circuit. And we want to be as minimum as possible. So in most cases, you'll be using R, maybe 4.7K, going upwards, so that the current is very much smaller than the 0.1 limit. And therefore, everything will be operating cold, and the power dissipation of the whole circuit means that the dissipation of the resistor plus the dissipation of the diode will be minimal, because normally when you're designing power supplies, efficiency is a factor, and then heat is actually normally a problem, in that the life of the components tend to decrease the more the currents are passing through, because the power dissipation of the resistor will be I squared R. The power dissipation of the diode is IZ into VZ. So the higher the value of R, the better. But it's actually a limit that you can increase it to before everything stops to work, that you can get from the data of the manufacturer. Okay, so this is how we make a reference, a simple reference circuit. Just use a resistor and then Zener. And you've gotten this part of your circuit. So you go to design it for stability and efficiency. Now we can go deeper and analyze the Zener in more detail. Now the Zener normally, its equivalent circuit normally has got an RZ, the dynamic resistance of the Zener, plus the Zener voltage, just like a diode will have a dynamic resistance inside it. Now the dynamic resistor for Zener, we call it RZ. That is just like even a voltage source. When you're studying practical voltage sources, the internal resistance is not zero. It will have some resistance inside. So similarly, a practical Zener has got an internal resistance. So this is the equivalent circuit, or be a reference circuit, taking into account the internal resistance of the Zener. So you can calculate IZ, the current that passes through the Zener, will be the supply voltage, in this case is V1 here, minus VZ. I've not written it over here, this should be VZ. This is your Zener voltage over the dynamic resistance, RZ plus that. And therefore the reference voltage will be equal to VZ plus the drop across RZ, which is IZ into R. So if you want to be very accurate, you got to take into account the dynamic resistance of the Zener. Now this dynamic resistance, you can only obtain it from the data sheet of a particular manufacturer. It will be small, but in most cases, we just ignore it to be zero. So for most of the problems I'll give, you can just ignore it. But if you want to be very, very accurate, you have to go to the data sheet and find out what is the dynamic resistance of the Zener. Okay. So that completes the analysis of your circuit for generating a reference voltage. So the next part of the we'll consider the sampling element. So for most of our cases, the sampling element is just simply obtained by using a potential divider setup comprising of two resistors. Either the voltage at the output of sampling element will just be beta V naught, where beta is R2 over R1 plus R2. So what's the function of the sampling element? So it monitors the output voltage and converts it into a level which is equal to Vref or near equal to Vref. A variation in the output voltage causes the feedback voltage. So this is a feedback actually. It's actually a feedback. So it causes the feedback voltage to change to a value which is either greater or less than Vref. In other words, for example, if you load in this circuit, in this block diagram, if you put a heavy load at the output over here, then this sampled part of the output voltage will decrease. If you release the load, then of course, this sample voltage will also increase. That's what I mean to say. So this difference voltage is the error voltage. It means the difference between the reference voltage and the sampled output voltage, the error voltage, which directs the regulator to make an appropriate response and thus correct the output voltage. So a practical implementation of the sampling element is to use a resistive divider. So the feedback voltage with feedback is just V naught R2 R1 plus R2. Or we can write that V naught. V naught. So since this voltage, normally if there's no output voltage, is equal to Vref. Vref can be written as V naught R2 over R1 plus R2, or you can rearrange it and put it in this form. It's no big deal. Anyway, the important thing is just that the feedback voltage is just V naught R2 over 1 plus 2, or V naught beta into beta, where beta is R2 over 1 plus R2. So I've just drawn it here. So this is the sampling element. I've just put resistance R1 and R2 to form a sampling element where beta is R2 over 1 plus R2. Therefore, the voltage going into we put it to the minus input is beta V naught. The voltage coming from our from our reference element, we call Vref, is Vz, and therefore the voltage at the output of our error amplifier, this is your error amplifier, is AD, this is the difference gain, Vz minus V naught into AD. So this voltage is used to drive our control element. So the third part of our system is the error amplifier. So the error amplifier is just this. So it monitors the feedback voltage and compares it with the reference voltage and provides gain for the detected error signal. The output of the error amplifier drives the control element to return the output to a preset value. What I mean to say over there is if the output voltage increases, if the output voltage here increases, it means that beta V naught is going to increase. Beta V naught is going to increase. And therefore, we want that Vz minus beta V naught into AD should be such that it decreases the output voltage. And the vice versa should also be true. If the output voltage decreases, beta V naught decreases, and therefore the output should drive the control element so that it increases the output. We shall do it with an example. It's actually very simple. And the final part, the error amplifier. I talked about the error amplifier. It's just an op-amp. Just use an op-amp whose characteristics are such that it's got little offset, with a good common mode rejection ratio, a good power supply rejection ratio, a low temperature coefficient, and a low output impedance, so that can drive the output circuit. But just basically no pump, Then the final part is the control element. The final part is the control element. Now, this is the important part that distinguishes whether our regulator is a series regulator, it is a shunt regulator, or it is a switching regulator. So I've said over here, so all the previous elements discussed remain virtually unaltered regardless of the type of regulator, i.e. linear or switching. This control element, this control element varies widely dependent on the regulator. There, what I mean is that you can use BJTs, you can use MOSFETs, etc. Now, this element is used to classify regulators as series, shunt, or switching. So this is the element that you look at to establish or identify that this regulator is a series regulator, or this regulator is a shunt regulator, or this regulator is a switching regulator. Because all the other elements are almost the same in all these regulators, apart from the control element. Next, I've said that the control element design also affects the minimum input to output differential voltage, the circuit efficiency, and the power dissipation. For example, if you're using a transistor, a BJT transistor, very efficient. If you use a MOSFET, it will be very efficient. Okay, that's why it's going to define the efficiency of your power supply and also the power dissipation. Now let's look at the topologies.
You can pick from there next time.
Charles, you're tired? Charles?
Yes.
You want us to stop over here?
Yes, I think it will be good if you can pick from there in our next class.
How many agree with Charles? How many agree? Let's vote.
The light group had a class, and
Yeah.
we have some material we are supposed to go through.
Okay, then we'll stop over there. Okay.